Hi, welcome back to my 4-part lecture series on science and media literacy. In part 1, I talked about what is science literacy. In this part, part 2, I talk about why does science literacy matter. Now in the previous talk, I finished up with a diagram that looks like this, and I made some points about the necessity of basic literacy and the importance of numeracy in science literacy so that people can make more informed health choices and also make more informed choices about the environment. Well, in this talk, I want to focus on the concept of numeracy in a little more detail. It kind of clarifies why science literacy is important. So numeracy is the ability to make sense of numerical concepts. At a basic level, this involves knowledge of arithmetic. Things like addition, subtraction, multiplication, division. If you're a more advanced student, then algebra and calculus. And at a higher level, numeracy involves intuitive reasoning about complex numeric ideas. Individuals with greater numeracy are better able to read, interpret, and apply scientific information. Now, much of the scientific information that people encounter is presented in a statistical form. Many studies on scientific phenomena represent the results as statistics. So understanding math is important, but having statistical literacy is also important. Statistical literacy is an application of numeracy. It refers to an ability to make sense of statistics and data. Individuals with this kind of literacy can more accurately judge statistical explanations of scientific phenomena. So I'm going to give some examples of how people dealing with scientific information may come to different conclusions depending on how they read that information and interpret it. So let's imagine we're trying to decide whether or not to take up cycling. And we ask ourselves, is cycling healthy? That's going to be an important deciding factor. Now, cycling involves physical activity, and yeah, physical activity is good for the health, definitely. But cycling also may involve risks of getting into accidents. Now, do those risks outweigh the benefits? If they do outweigh the benefits, maybe we won't take up cycling. Well, if you live in Europe, then there's a lot of infrastructure for you to cycle separate from cars. A lot of cities in Europe have dedicated bike paths, and so cyclists can ride there fairly safely, and the benefits of cycling probably outweigh the risks. But this isn't necessarily the case in the United States, where there is less infrastructure for cycling. And some researchers actually looked at the risk of cycling in the US. They found that per 1,000 kilometers traveled, you are 10 times more likely to die on a bicycle than in a car. So obviously, if you're in the United States, you shouldn't cycle because it's extremely dangerous, right? Well, here's another statement based on the exact same data. Per 1,000 kilometers traveled, there are 0.00004 more bicycle deaths than automobile deaths. So if you're going to travel 1,000 kilometers and you choose a bicycle over a car, your risk of dying increases by that much. Not so much, is it? But how do these two statements reflect the same underlying data? How is that possible? Well, as it turns out, the risk of dying in a car accident is like 0.0000. There are a bunch of zeros. There's a super low risk. So 10 times that still has a bunch of zeros in front of it. It's still a super low risk. Yeah, it's 10 times riskier, but 10 times almost nothing is still almost nothing. But you can see how very different conclusions can be drawn from these two statements. Now, somebody with good science literacy might encounter either statement in isolation and wonder about the raw data. How can they draw their own conclusions from the data, right? But somebody with low science literacy, low statistical literacy in particular, might not make that sort of evaluation and might be influenced by, if they only see one or the other, that will ultimately impact their decision. Here's another example in the environmental context. So earlier I talked about ecological literacy, and yeah, people make stats-based decisions about the environment as well. Is rising sea level a problem? Well, according to the Intergovernmental Panel on Climate Change, by the year 2100, sea levels will have risen an additional 25 centimeters. That's quite a significant rise if you are a poor farmer living in a low-lying coastal area where in the future a 25-centimeter rise in sea level will mean that seawater will inundate your farmland and make it very difficult to grow food. That's certainly a problem, but what if you're the ocean? Well, ocean depth is projected to increase by only 0.007% by 2100, because of course the ocean is quite deep and 25 centimeters really isn't that much of it. And so it's easy to say, well, yeah, sea level's rising, but it's minuscule considering the size of the ocean. Now, depending on your level of numeracy and science literacy, you might come to very different conclusions from these two statistics, right? And so people's numeracy, their statistical literacy, can affect how messages like this impact their beliefs. All right, one more example. Is shark fin soup bad? Bad implies a moral judgment, and there is a moral issue here. It is inhumane, it is wrong to be treating animals like that, right? There's something just wrong about that. It is bad. But aside from these morality-based judgments and these feelings about shark fin soup, there's also a scientific reason why shark fin soup is bad. Sharks are apex predators. They are essential to ecosystem maintenance. And killing millions and millions of sharks creates problems for ecosystems. It can disrupt food chains, create imbalances. And so then it becomes a problem if we're killing a lot of sharks. So how many sharks do we kill every year? Well, it's estimated we kill 100 million sharks per year. Just think about that. Imagine 100 million sharks. Think about each one of those 100 million sharks, and you probably can't. 100 million, I think for most people, is a number that really defies concrete understanding. It's this abstract concept that we understand. We know how to analyze it in math equations, right? We know what 100 million means, but we don't know what it looks like. So we could put it down on a weekly basis. That's about 2 million sharks per week. 2 million is still a huge number. Maybe the most mathematically gifted minds can visualize 2 million things, but this is still abstract to most people. What is 2 million actually? All right, so let's look at it per day. 100 million sharks per week is around 300,000 sharks per day. Now, there are some major events throughout the world, concerts, sporting events, that draw crowds of 300,000, and I've seen these on TV. I know what a crowd of 300,000 people looks like, but it's still just a sea of people, and where do the individuals separate from the masses? How about 10,000 sharks per hour? I've been to many sporting events with 10,000 people, and I know what that looks like, and I can visualize 10,000 people. That makes sense to me. Now, people with really great numeracy, really intuitive understanding of big numbers, they might be better at one of these higher levels, but for me, maybe 10,000 is about the biggest number I can deal with. Of course, for some people, numeric representation, just the raw number, won't really help them. This is where things like infographics come in handy. This infographic was going around on the internet a couple years ago, and it shows basically how many people die by sharks every year versus the number of people that sharks kill every year. And it visualizes, sorry, not every year, every hour, number of sharks killed by people every hour, and it visualizes 11,000 something hundred sharks. And it really creates an intuitive sense of that scale because this infographic is gargantuan. And so by presenting the statistical information that way, even people who don't have an intuitive sense of what 10,000 means can start to appreciate the scale of this problem. Now, what this example really shows isn't that people need to have statistical literacy per se, but that the way scientific issues are communicated need to speak to people in a way that's relevant and meaningful to them. But even the previous examples of the two versions of the statistics, that shows that communication is absolutely important. And in one paper, it was said that learners typically receive smatterings of environmental information rather than building a deep cumulative knowledge of underlying principles. This lack of proper attention to environmental fundamentals makes the media in its many forms the most powerful tidbit provider, and thus both a positive and negative force in the dissemination of environmental information. It turns out communication and the media are very important because the knowledge from scientists gets filtered through the media very often before it reaches the public. And so here's where science literacy kind of fits into this bigger picture. So I'm going to go out on a limb here and say that scientists have science literacy. I didn't really go out on a limb. Of course, scientists generally have good science literacy. And in this lecture, I argued about the importance for the public to have science literacy so they can interpret information that they encounter and have good statistical literacy when that information is based on statistics. But a lot of the times, the information the public receives has been filtered through the media, and so it's really important for people in the media to also have science literacy so they can interpret the information and the process of science that the scientists did, and then present it in a way that's meaningful and useful to the public to engage in thinking about these issues and engage in discourse with each other. Now, of course, the relationship among science, media, and the public has a lot to do with how scientists and the public view the media and how they think about media processes and media effects. That's all about media literacy, which I will talk about in part 3 of this series. I mentioned a couple studies in this lecture. If you're curious about reading those, I've included links in the description. Otherwise, I'll see you in part 3. Thanks for watching.